welcome to the class once again. I hope you are all doing good and you're the best of your health. So after watching all the classes of rotational motion and system of particles, I believe that you'll be ready to solve questions. As advised in the regular classes, I have told you to practice questions simultaneously with each of the topic covered. We have done with moment of inertia concept, we have done with how to find out the center of mass. Today we will practice some questions based upon rotational concept and center of mass, and that will be based upon the pattern of JEE main pattern exercise. Already the 5 questions we have done. Now let's proceed with the next 5 questions, that is from question number 6, and you already know that question will be of single choice objective question. Let's go ahead with the question number 6. A child is standing with folded hands at the center of a platform, rotation about its central axis, that is, it is rotating about its central axis. The kinetic energy of the system is K. You can see that the child and platform which are rotating together, they have the kinetic energy given as K. The child now stretches his arm so that the moment of inertia of the system doubles. I have discussed this kind of problem in our regular classes with an illustration. I have told you if a child rotates on a circular platform, if he stretches his hand, he'll find that its moment of inertia will increase and hence its angular velocity will decrease. We'll talk about how this is actually possible because angular momentum will be conserved. Now next point you see, we have to find out the kinetic energy of the system now is A 2K, B K by 2, C K by 4, D 4K. That means we have to relate the final kinetic energy of the child and platform system with respect to the initial kinetic energy. I hope that you are remembering how this is related with the child and circular platform on which it is rotating. Now you see that this is the circular platform. You can see that, and we have discussed already such kind of problem. The child is standing on the platform. Let's say initially the hands were like this. This was the initial position, and given that in this position the moment of inertia is given as I. This is the moment of inertia in the initial state. Child is standing with folded hands at the center of a platform, rotating about its central axis. This is rotating. Don't think that it's rotation. Rotating about its central axis. The kinetic energy of the system is K. So let me say that kinetic energy of the system is K. This is given as. Now we have taken that initial moment of inertia is I, initial kinetic energy is given as K, and next you see that the child now stretches his arm so that the moment of inertia of the system doubles. Now if the child stretches the arm, we all can understand that this is the axis of rotation. If he stretches the arms, that means the mass distribution from the axis will be at a distant point. Its distance will increase. If distance will increase, then what will happen? The moment of inertia will increase, because we all know that moment of inertia is given that I is equal to mr square. This is what we know, that each point mass, its distance from the central axis. We can see that as distance will increase, moment of inertia will increase because mass will remain same. And you know why I have written this? Because each of the point mass we have to add and then we have to give the moment of inertia accordingly for this system. Now it says that moment of inertia doubles. Let's say on stretching his arms, the moment of inertia becomes, so first of all, initial with hands folded, moment of inertia mi is equal to I. On stretching arms, that is with stretched arms, the moment of inertia is given as 2I. This is what that has been given in the problem statement. The kinetic energy, how it is related. Now see, there is no external force on the system, there will be no external torque acting on the system. That means angular momentum will remain conserved, as we have discussed. Since torque external is equal to 0, angular momentum remains conserved. So let me write down this statement. Angular momentum remains conserved. This is what we can write about the child and platform as a system. Angular momentum remains conserved. So if angular momentum remains conserved, we can write that Li initial is equal to Lf. That is I into omega, that is the initial angular momentum, will be equal to 2I into omega dash. So let me write down here, I into omega is equal to 2I, this is the final angular momentum, that is what has been provided, multiplied with, let's say, final angular velocity is omega f. So omega f will come out to be omega by 2. So we got first of all this thing. Now this is a case of only of rotation. So we can think about, we can talk about, we can understand how the kinetic energy will be expressed. The kinetic energy will be given as kinetic energy, that is K, that will be half I omega square. This was the initial kinetic energy. We have to talk about the final kinetic energy. The moment of inertia and both the angular velocities have changed. Let's put up their changed values. So let me put up the values for the final value of moment of inertia and angular velocity. So final kinetic energy will be KEF is equal to half, final moment of inertia is 2I, and omega is, omega final if I use, that is actually omega by 2, but before that let me use omega final whole square, half into 2I multiplied with omega final, that is omega by 2 whole square. Clearly you can see that we will be having the required relation will be pretty much clear to us, and we can relate half I omega whole square here, and this will come out to be, this 2 and 2 will be cancelled out, will be having 1 by 4 I omega square. That is, this is 1 by 2 of half I omega square, 1 by 2 of half I omega square. This value is the kinetic energy, initial kinetic energy, that is K, so half K. That is final kinetic energy is half times of initial kinetic energy. That is what we have learned with this example. So we have performed, we have actually solved the question going through which each steps elaborately. In your exam you can actually solve it with quite speedily. You can do that if you know the method. You can just conserve the momentum, write down how kinetic energy is related with angular velocity. You can understand that on conserving momentum, as momentum of inertia doubles, the angular velocity will be reduced to half. Put up the values, you will get the kinetic energy that is reduced to half. Let's check the option. This is a previous year mains question, so you need to know how to solve such kind of question. A incorrect, B is the correct question, correct answer, C incorrect, D incorrect. So I believe that you would be having an idea now what kind of questions can be asked in your JEE main examination. So not too tough if you are very much aware of the concepts. That's why I advise you try to have an idea about each of the concept in our regular sessions. The concepts, you may think that this is avoidable, but you have an idea about it. An easy question comes based upon it, you can easily solve it. Let's go to the next question of the day. Question number 7. A rigid spherical body is spinning around an axis without any external torque. Again, it says that rigid spherical body. That means it's a case of solid sphere. Due to the temperature, its volume increases by 3%. Due to temperature, its volume increases by 3%. That means temperature is raised, volume is increased by 3%. That is what we can understand. Then percentage change in its angular speed. Again, understand this statement, spinning around without any external torque. I hope that you can make out from this statement, if no external torque is acting, that means angular momentum will remain conserved. So first statement I am writing here from the first given information, external torque is equal to 0, therefore angular momentum will remain conserved. So I am not writing the entire statement. Li equals to Lf, initial angular momentum is equal to final angular momentum. That is what we can make out from first statement. Due to temperature, its volume increases by 3%. If volume increases by 3%, so can we find out with what percentage there will be change in radius of the body? Because we know that moment of inertia of a solid sphere is 2 by 5 mr square. So we'll be using that. But before that, let's try to find out what is the change in its radius. So here we have, first of all, volume is given as 4 by 3 pi r cube. So if we write delta V by V, I have taught you about this, how to actually find out this. This 4 by 3 pi will remain in the same way, constant, you need not to worry. 4 by 3 pi will remain the same way, and this will be 3 times of delta R by R. Or let me talk about only about the constant terms. 3 times of delta R by R, this is the term that we will be getting. Now we have to talk about the change in volume is 3%, that is what that has been given. So delta V by V multiply by 100%, this is equal to 3 times of delta R by R multiply with 100%. This is what we can do. Delta V by V into 100%, that is given as 3%. So 3 times of delta R by R into 100%. So what will be delta R by R? Obviously that will be equal to 1%. So let me write down, since delta V by V into 100% is equal to 3%. So therefore easily you can make out delta R by R will be what? That will be 1%. Delta R by R multiply by 100%, this will be equal to 1%. That is, the radius will be increased by 1%. Now we got what will be the change in the amount of radius. Next statement you see, then percentage change in its angular speed. We have to conserve the angular momentum now. Now come the main part. We have to conserve the angular momentum. Angular momentum is I into omega. Let's use it. Now moment of inertia will change, quite obvious. So first of all, let's say initial moment of inertia we are going to express with I, and final moment of inertia we are going to express this, let's say, with I dash. Initial moment of inertia, just to see, it will be given as 2 by 5, let's say its mass is m, mr square. This is what we know about the moment of inertia. Radius has changed to 2%, sorry 1%. Let's talk about with what amount the moment of inertia will change. Now you see here, delta I by I, in the same way delta I by I into 100% will be equal to delta R by R, and since we have R square, so 2 the coefficient will come here and it will multiply twice of delta R by R into 100%. This is what we have here. This value we need to find out. Delta R by R into 100%, that is 1%, so this will be equal to 2%. So delta I by R into 100%, that is equal to 2%. That is, the moment of inertia, if the volume increases by 3%, the moment of inertia will increase by 2%. We got this. Now conserve the angular momentum. When you talk about the conserving the angular momentum, as initial angular momentum is equal to final angular momentum, so I into omega, let's talk about I initial into omega initial is equal to I final into omega final. This has to be conserved. Now you have to think logically. Moment of inertia has risen by 2%. To keep the value constant, this value is constant because the angular momentum remains conserved. To keep the value constant, angular velocity has to decrease by 2%. That means there will be reduction in the angular velocity by 2%, since you have to keep and conserve the angular momentum. Since I increases by 2%, there will be a reduction in angular velocity. Angular velocity reduces by 2%. So that angular momentum remains conserved, angular velocity has to be reduced by 2%. Let's talk about the solution. You see here, its angular change percentage and in angular speed, it will be minus 2%, yes, because there is a reduction. Rest B, C, D are incorrect. I hope that you would have understood how to solve such kind of question. With each statement, you have to verify and understand what equations to use to actually reach to the subsequent steps employed in solving the question. I hope that you have got it, how to solve such questions. Let's go with the next question of the day. I hope you are getting and you are understanding how to solve all this, and you will be finding it quite easy and helpful. Let's go to the next question. 8th. ABC is a right angle triangular plate. You can see ABC, right angle triangular plate of uniform thickness. It says that is a plate. Don't think that is a rod. It's actually entire solid plate. You can think in this way. I1, I2, I3 are the moment of inertia about AB. So we have moment of inertia about AB as I1. Let me mark here. Moment of inertia about AB as I1. Then we have I2 about BC. I2 about BC and I3 about AC. This is what has been given. Check the statement. I1, I2, I3 are moment of inertia about AB. So about AB I1, about BC it's I2, about AC it's I3. Then which of the following relation is correct? A, I1 equals to I2 equals to I3. B, I2 greater than I1 greater than I3. C, I1 will be greater than I2 will be greater than I3. This is what has been given. And D, I3 greater than I1 greater than I2. This is what that has been given in the options. Now we all know that, understand, moment of inertia is sigma mi ri whole square. This is what we have learned, where I starts from 1 to I equals to n, as many number of particles are there within the system. For a continuous, for any distributed mass system, you can actually employ this formula. That means the distance of the point mass from the axis decides the moment of inertia. How the distribution of mass will be there from the axis, that will decide the moment of inertia. That means if the axis is closer to each of the point masses, the moment of inertia will be lesser. If the axis of rotation is farther away from the mass distribution, that means the moment of inertia will be larger. Now try to understand how to understand this I1, I2, I3. See that it's given, this angle is 37 degree. Let me rub this part. This angle is 37 degree. So we can compare the ratio of the lengths. So if I make this triangle that has been given, this is given as 37 degree. So if I compare the ratios, I am not writing the exact length. If I compare the ratios of the three lengths, we can say that they will be in the ratio 3, 4 and 5. This is what we can actually make out, 3, 4 and 5. Now quite easily you will be having the idea about the moment of inertia. You see here, this entire body is solid. From this axis AC, the entire mass will be closer. Just try to compare the mass distribution. From AC, it will be closest, the mass distribution. From AB, that is the axis of the least size, the mass distribution will be further away from it. Then if I talk about BC, the mass distribution will be comparatively not too far away, not too close. You have to use logic. I cannot show you any equation here to actually justify my statement. I am saying to think and logically reach on the conclusion. Now see, if I write this statement, from AB, mass distribution will be farthest. Mass distribution will be farthest, as it is the axis of least size. Mass distribution will be farthest. Next you see, from AC, we can write about this is the axis of the longest length. Mass distribution will be closest to this axis AC. So from AC, if we write, from AC, mass distribution will be closest. This is what we can make out by just visualizing the figure, the picture, the arrangement that has been given. Now somewhere in the middle, the mass distribution will be somewhere in the middle as compared to axis AC and axis AB. For BC, the mass distribution will be somewhere in middle. So we can see that, as I have written that, moment of inertia depends upon the mass distribution. The farther the mass distribution from the axis, we are talking about the same point masses for each of the three axes. One axis is AB, one axis is BC, one axis is AC. Moment of inertia for AB is given as I1, for BC it's given as I2, for AC it's given as I3. Since mass distribution is farthest away from I1, I1 will be the largest. Then we'll be having I2, then the closest mass distribution, that will be I3. So I1 will be greater than I2, will be greater than I3. This is what we can make out. So I1 greater than I2 greater than I3, option number C clearly matches. So let me mark this option as the right answer. Rest you see, they won't be equal. Here you see this are I2 is greater than I1 greater than I3, that is incorrect. Here I1 greater than I2 greater than I3 is just now we reached on to this state on this option, so this is correct. I3 greater than I1 greater than I2 incorrect. So from this example, we can understand there won't be always equations for you to reach on to the answer. If you think logically, you can understand how to approach and how to actually reach on to the final answer, that is the final result. I hope that you have got how to solve such kind of question. Next thing, let's proceed further. Next question of the day, question number 9. A ring of mass m and radius r. You can see that this is a ring, its mass is m, its radius is given as capital R, has 3 particles attached to the ring as shown in the figure. 1, 2, 3, 3 particles we have. The center of the ring has a speed v0. This is the center of the ring, it has a speed v0, so let me mark its speed as v0. That is center of mass, speed is given as v0. The kinetic energy of the system is, slipping is absent. A 6 m v0 whole square, B 12 m v0 whole square, C 4 m v0 whole square, D 8 m v0 whole square. In this question, let me tell you one thing. First of all, already I have discussed about such a case. When on a ring there are certain masses, I have not placed mass, I have told you what is the velocity of each of the points distributed on the circumference of the ring. On the periphery of the ring, the mass is what point, how to find out its velocity. I have discussed about all this. Now this is actually in rolling motion. It's in rotation also, it's translating also. So such kind of motion is rolling motion. So let me discuss first of all the concept of rolling motion here. In this case, how it will be applied here. This ring actually traverses with a speed v0 towards forward direction. It's rolling. This is what is happening. So we can say that the angular velocity omega naught will be equal to v0 by r, where r is the radius. First thing we can write about this, v0 by r, that will be equal to omega naught. Now you see, if I mention the points, let's say this is point A, let's say this is point B, let's say this is point C. Let's write the velocity of each of the points. I have discussed about how to find out the velocity of point A, B and C in our one of the regular session. If you have watched it, you can clearly understand how to evaluate it. For point A, see that what will be its velocity. The ring is rolling, it's having a linear velocity v0. This point will be having, let me show you with this color, will be having a velocity v0 here. So v0 here this end and v0 here this end, both are at 90 degree. Its net velocity will turn out to be v0 root 2. This will be net velocity, that will be root 2 v0. This is what we can make out. So for point A, net velocity will be equal to root 2 v0. Similarly for point C also, it's rolling, so you'll be having two velocities, v0 here and one v0 here. So net velocity will come out to be root 2 v0 at this end. So for point C also, net velocity will be equal to root 2 v0. We got it? Clearly you'll be remembering about the point's B velocity. Point B velocity will be equal to twice of the velocity of the center of mass, that is, it will be 2 v0. So for point B, this will be, its velocity will be equal to 2 v0. I have written down each of the individual velocity and how it has come. Due to rolling, it will be having one velocity v0, and due to the linear motion, it will be having one more velocity, that will be v0. So net velocity will become 2 v0 for point B also. I have written down. Now kinetic energy of the system will be due to the ring, due to the mass kept at A, due to the mass kept at B, due to mass kept at C. Now let us place each of the masses 2m, m and m. So let me write down, this is 2m, this is m, and here also we have kept m. Now you see, let's write down the kinetic energy of the entire system. We will be having kinetic energy. First of all, it will be due to kinetic energy of ring, kinetic energy of ring plus kinetic energy of mass 2m kinetic energy of mass 2m placed at A plus kinetic energy of mass m placed at B plus kinetic energy of mass m placed at C. We can write down this equation to actually tell how the kinetic energy will be evaluated. Now you see kinetic energy of ring. Kinetic energy of ring will be equal to, due to its rotational motion and due to its translational motion, that is half m v naught whole square plus half I omega whole square. So half, and the value of I, to actually reduce this step I am writing directly the moment of inertia of ring. We know that it is mr square. So I am using m, its radius r square, its omega square we have to write. So we can write v naught by r whole square. Kinetic energy of 2m placed at A, its kinetic energy will be half into mass, its velocity root 2 v naught whole square, plus you see a kinetic energy of mass at B, that is half m root 2 v naught whole square, plus kinetic energy of mass at C, so half m 2 v naught whole square. Now clearly you can actually solve this. You have to just reach on with the calculation. Let me rub this part, because already I believe that you would have noted down this part, and let me write down the final value. See here, half mv naught whole square, this r square will be cancelled out, plus half mv naught whole square will be having mv naught whole square. From here and here will be having mv naught whole square. Now you see, this 2 and this 2 cancels out. Here you will be having root 2 whole square will give you 2, so 2 mv naught whole square. So first of all, we had from here mv naught whole square plus 2 mv naught whole square. Here you see, here we are getting 2 and 2 will be cancelled out, you will be having mv naught whole square. So mv naught whole square plus 2 mv naught whole square plus mv naught whole square. Let me write down everything so that you do not get confused. Kinetic energy will turn out to be mv naught whole square plus twice of mv naught whole square plus mv naught whole square, plus here you will be having again 2 mv naught whole square. 2 mv naught whole square, this turns out to be 6 mv naught whole square. Easy, simple, we have done this. So each step we have employed to actually reach on to the final kinetic energy of the system. And with practice you will find that accuracy will automatically come to you, and then automatically you will reach to the speed, and such question you can solve with speed and efficiency. Let's go ahead. I hope that you have understood how to find out the kinetic energy of such a system. You have to individually evaluate the kinetic energy of the entire particle which actually constitutes the system. That is what you have to do in such kind of question. Let's go to the 10th question. Question number 10. A solid uniform sphere rotating about its axis. We have a solid uniform sphere. That is, it's a solid sphere rotating about its axis with kinetic energy E1 is gently placed on a rough horizontal plane at time t equals to 0. That means you have taken a sphere, you have gently placed it on a rough sphere at time t equals to 0. That is the start of the system motion. Assume that at time t equals to t1 it starts pure rolling. Now initially what will happen? Initially it will rub against the surface. You see here what is happening. This is the rough surface on which you have placed a rotating sphere, and it's rotating. Then what has happened at t equals to 0, we placed t equals to 0, it was placed. Now what will happen? Initially sliding will happen. Initially from t equals to 0 to t equals to t1, sliding takes place. Sliding takes place. From t equals to 0 to t equals to t1, sliding takes place. That is what we can actually frame out from the given statement, because it is kept. It starts pure rolling after time t equals to t1. That means till the time less than t1 it was rubbing against the surface. It starts pure rolling, and at that instant total kinetic of the sphere is E2. So at T1 the total kinetic energy is E2. Let me write down. At T equals to 0, given that kinetic energy is equal to, given as K1, kinetic energy is given, sorry, E1, that is given as E1. At T equals to T1, given that kinetic energy is equal to E2. Next thing you see, since it was rubbing against the rough surface, when it was rubbing, that means it has to, friction will do some work on it, that means its kinetic energy will be reduced. Try to understand. Logic, I have explained you this in work energy chapter. When a resistive force works on a body, that means its kinetic energy will be reduced. That means we can make out one thing, that E2 will be less than E1. Now you see further, after some time, at time T equals to T2, kinetic energy of the sphere is E3. Pure rolling starts and pure rolling continues. That means angular velocity will not be changed, linear velocity will not be changed. That means kinetic energy will not change, that will remain conserved. So at time T equals to T2, given that kinetic energy is equal to E3, as no change in angular velocity, and since in pure rolling, understand, friction will do no work. In pure rolling, friction does no work, as no change in angular velocity and friction does no work, kinetic energy will remain conserved. Kinetic energy will remain conserved. What does that imply? If kinetic energy remains conserved, that is at time T equals to T1 and time T equals to T2, the kinetic energy will be same. That is E2 will be equal to E3. E2 will be equal to E3. We can make out what from comparing all the three energies at different time instant. E1 was the highest, then came E2 and which was equal to E3. We got it. E1, some energy was lost and then E2 was reached, then that is equal to E3. So let me write down, let me actually make out, since I believe that you would have taken down the statement, let me rub this. We can write down E1 is the max, that is equal to, that is greater than E2, and E2 is equal to E3. So let us check whether it's which option matches. E1 equals to E2 is equal to E3? No. E1 greater than E2 equals to E3? Yes. This is what we have taken down. C, E1 greater than E2 greater than E3, so incorrect. E1 is less than equals to E2, E3, so incorrect. Only option that is correct, that option will be E1 will be greater than E2 will be equal to E3. This is what the option that has been given to us. So I believe that all this set of 5 questions will be very much helpful for you all in your understanding of the concept. What you do, you practice more questions based upon moment of inertia, based upon rolling, and you will find that this exercise will be very much helpful for you all. And I believe that you have watched the entire sessions, because that is required. Try watching all the lessons so that your understanding and your application of the concept will be quite easy for you all. So thank you everyone, wish you all the very best. I will meet you all in the JEE Advanced exercise in the next class. Thank you everyone, bye-bye.